So let's start with another lecture today, which is static timing analysis. Okay, so what is static timing analysis? So first let's try and recap what we learned in the earlier classes. Timing constraints. Okay, so there were two types of timing constraints. One was known as setup time and the other was hold time. So setup time is like when the clock is going positive high. Okay, before that the data needs to be stable. Okay, by the setup time. Okay, if the data is going to change after the setup time, before the arrival of the clock, then that data may not be captured by the register, right? So we saw in detailed, so that depends from register to register, how the registers are made up of. That we saw for different kind of registers, the setup times are different. Okay, similarly, after the clock is going high, the D needs to be stable for some time. Okay, so they may be hold time, they may not be hold time for different kind of registers. But let's take a universal case where there will be some hold time. So you need to hold the data for some more time. Okay, till and then only you can change the data, right? So when the clock is going high, the previous data what was there, that needs to be kept stable for some more time. So there comes the hold time. And then another important figure of merit will be of an register will be the delay. Okay, propagation delay, that is from clock to Q delay, that is known as. So when the clock is going high, right, for the data to be reflected at the output, there will be some propagation delay. So only after TC to Q, the data will be available for the next stage to capture the data. So not that the moment you have given clock high, you start capturing the output data. So you have to wait for this much duration for the data to get stabilized. Okay, so these are the three things which we should know. Now clock skew, like we studied in the last class also, because it is like the same clock skew is the clock coming to the different flip-flops at different times. Okay, because of in between there could be unequal number of buffers, or the wire lengths could be different. Okay, so that is clock skew. Clock skew is the same clock arriving at different flip-flops at different times because of delays in the path. Okay, so there could be unequal number of buffers in between, or the wire lengths could be different. Okay, a clock jitter is the same clock, the clock arriving at the same flip-flop, but every time it may not reach at the correct time, right? Okay, it could vary a little bit here and there because of the clock generation circuit itself. Okay, because of the temperature issues and things like that, the VCO itself, there could be some jitter. So that is jitter. Both these together can be called as a clock uncertainty. Okay, so clock uncertainty is nothing but clock jitter plus clock skew, right? So if you see here, this is the ideal clock here. So there is a jitter out here, right? The clock could come here, or it could come here also. Okay, so this is or in a more generalized time, I could call it as a clock uncertainty. It could come here also. The clock could come here also, right? So this is the ideal clock. This is with the jitter. The clock is coming early. Instead of coming here, it has come early out here. So if the clock is coming early, so I have to cater for that much setup time, right? So if suppose this is the setup time required, now the clock is coming early, so this setup time, now I have to cater for a greater setup time now. Okay, because setup time violation has occurred here, because this much time was required actually. So that was good enough for the if the clock had arrived in the actual time, but since the clock has arrived early itself, the setup time has got violated in this particular example. Similarly, a clock coming late, okay, can violate the hold time also. Now this was the original clock here. The data is changing after this. So this was good enough time. Okay, a hold time we had catered for. But because of clock jitter, this clock is coming late. So now you will have a hold time violation. So whenever we check for these kind of things, we have to be careful when we decide design a circuit. We have to not only cater for hold time and setup time, we also have to cater for the clock uncertainties. Okay, So that also needs to be taken. So there are two main problems that can arise. One is known as the max delay. So the data doesn't have enough time to pass from one register to the next before the clock edge. Okay, so that you have to take care. That is known as max delay. Similarly, the data could be passing very fast. That is known as minimum delay. So the max delay, okay, can cause setup violations, and the minimum delay can cause, okay, the min delay violations can cause the hold problems. Okay, so it will be clear when we take few examples. Right now, if you see here, this is the clock going high out here, right, and this data is changing out here. So you have one flip flop. This is the second flip flop. Here this clock is being fed. The same clock is being fed to both the flip flops out here. So this output is available A. So some logical function. This is a pipeline structure. So this is some logical block is here. It could be some set of some gates. Okay. So there will be some delay from here to here. Right. So now if you see here time. Okay. You have to set up a time or a frequency for this clock in such a manner. This is going positive, right? Now from here to here there will be one delay. From here to here there will be one delay, right? Plus you have to give some time for the setup also. So this t has to be greater than here to here, and before the next clock this data has to settle. So you have t setup also. Is this first equation clear to all of you? It's very important. Based on this only most of our problems, numerical problems will be able to do. Is the first equation clear to all of you?
Yes, Professor.
Yeah. Okay. Now, if you say there is some skew in the circuit, okay, so you have to cater for that skew also. So you add that skew also out here. Okay. If there is a skew, I add one. Clock uncertainty. If I know, okay, there will be some 1-2 nanosecond uncertainty in the clock, so my time period should cater for that also. So I increase the time period, right? And also if I want to give say 10% margin, like when I design the circuit, I might put some margin. I might want to put few picoseconds margin, because during fabrication, okay, during layout, there could be some additional errors which can happen. Okay. In the suppose when we are implementing this logic, initially during the schematic and the layout configurations, I am getting some 100 pico, but then when I am actually making it in silicon, it could increase from 100 to 102 or 103. So I can take some amount of margin also. So this will put a more realistic equation to follow. Okay. Now what is setup slack? Okay. So data required time. Yeah, tell me.
Why is delta skew is in the left hand side of the inequality, which should be on the right hand side, like you are adding some delay to the period, okay? Like you are increasing the period.
Yeah. Here it is, since it's in a greater sign, so this will also result in increase in time only, right? If you take this margin.
Yeah, margin is understood, sir, but why there is delta skew you are putting on the left hand side?
It doesn't matter. You can put it here also, because there is a greater sign. You can put it anywhere. It doesn't matter. Right? If you put it here also, it doesn't matter. Okay. So now, what is the setup slack? Okay, it is the data required time. Okay, minus the data arrival time. Okay, this is the minimum time. So this is known as, if it is positive, then there is no timing violation. If it is negative, there is a timing violation. So this is the case which I have taken. So for every circuit, we have to see that this particular condition is met. Okay. So I do t minus this much. Okay. If it is positive, that means there is no, what is positive slack? This t minus this sum of these three. If I, right now we just forget about this skew and margin. If I take this particular top equation, t minus this much, sum of these three should be positive. That means it's a positive slack. Then it is good for me. So no timing violation. Negative slack means t minus this much is coming negative. that means there is a timing violation. Then I have to insert some additional blocks or modify my circuit. Okay, so that is what it has to be done. Similarly, there could be a minimum hold constraint. Okay, what is a minimum hold constraint is it is the same clock. Now I am considering the same clock here. For the setup time, I am considering one clock to other clock. For the hold time, I am considering the same clock. This clock is going high, this clock is going high. When this clock is going high, this data at B will change. Okay, but it should not change very fast. It should cater for the hold time of this flip-flop, right? That means the delay from here to here, right, and the delay from here to here, right, should be greater than T hold. Is this top equation clear to all of you? Right? Here I am talking about the same clock. Remember, it is the same clock. Previous I talked about one clock to other. Hold time is always about the same clock, right? Now, what are these flip-flops are supposed to do? They are level triggered, right? When the clock is going high, whatever is the data here, that needs to be captured. The previous data which is available, not the new data which is coming here. That's how flip-flops work, right? The previous data itself it has to capture, not the new data. So during edge, because they are all edge triggered, so it is capturing the new data. But this B has to remain stable for some more time, okay, for a period defined by T hold. So T hold. So now TCQ plus T logic has to be greater than T hold. So this is the hold time logic. Is it okay with all of you? Right? Yeah. So now
Yes.
same margin and skew you can put in these equations. Otherwise, the positive slack will be this minus this. Okay, TCQ logic minus T hold, no timing violation.
T hold for first flip flop or T hold for second flip flop?
Second flip flop, for the second flip flop. Okay, we are seeing the hold violation here at the output. Like for the setup also, we were talking about this only. Yeah, tell me. Okay. Okay, so let's.
In the field, when we were considering the
Yeah, tell me.
previous one.
Yeah.
Hello.
Yeah,
So
yeah.
the previous one, yes, sir. Sir, what is the difference between the clock condition here and in the while we are just considering the hold time? Because here also the same clock is being fed to both the flip flop.
No, here for the setup time, okay, we are talking about this time here. The data needs to be stable before the clock is going high, right? In the other case, we are talking about after the clock is when the clock is being hold time. In the hold time, okay, we are talking when the clock is going high, right? After the clock is going high, the data requires to be stable for some more time. So that is the issue there. Is it okay? So let me come back here. In the first case, okay, this clock is going high. Now this data requires to be stable before that. Okay, now I am talking about this data coming from here to here, right? From here to here. So this, and then the whole time the data has got settled till the time the next clock is coming high, right? So I have this time also out here. Okay, the data has passed from this flip-flop and this flip-flop and this logic, and it has settled also before the arrival of the clock. So I get this equation. So that is setup time, right? Whereas in the hold time, okay, this clock is going high, this clock is going high simultaneously. Now I am talking about a situation. This clock is going high, but this data should not change for a duration defined by the hold time, right? But since this has gone high, there is a change in data which is happening here. There is a change in data which is happening here. That now I am saying that should not come here very soon. So I am imposing a restriction there, a hold restriction, so that this delay plus this delay has to be greater than the T hold. So this is the second set of restriction I am holding, which I am imposing, which will be known as hold time restriction. Is it okay?
Yes.
Okay. Okay. So let's take one example out here. With this, things will be even more clear. Okay. So we are talking about this final stage here. Let us talk about the we are talking about the minimum clock path, how fast the clock will reach here, okay, to find out the setup slack. So I have this clock here, okay, 2 nanosecond is the time taken in this particular wire section, 5 nanosecond is the time which will be taken, right, 50 nanosecond is the clock period itself, okay, that also you have to cater because, right, for the setup time. So 50 nanosecond is the clock period, plus 2 nanosecond is the time taken in this particular wire, 5 nanosecond is the time taken in this particular buffer, 2 nanosecond is again in this in this particular wire, and I am subtracting the setup time out here, right, because that much time is not available to me. So this is the minimum clock period, or I can put this 4 nanosecond here as positive also, doesn't matter. So I am putting it here as negative. This is the setup clock path delay minimum. And what about the data? In the data I am going to take the maximum data arrival. So here if you see here, this clock out here, okay, 2 nanosecond for the clock to reach from here to here, 2 nanosecond, from here to here again 2, from here to here 9, from here to here 2, right. So if I see here, it is coming out to be negative, okay, that means there is a setup time violation, right. So the clock from here to here, okay, is going to reach at 15 plus 2 plus 5 plus 2 minus 4 is scattering for the setup time, right. So this data should ideally be within 20 seconds, within this 20 seconds this data needs to be stable here, including the setup time. This data should be stable here at 20 seconds, right, 20 nanoseconds. But actually there could be a possibility that if I take the max times 2 nanosecond plus 11 plus 2 plus 9 plus 2, it could take as long as 26 nanosecond. So this particular circuit has got setup time violation, okay. So if I have to overcome this problem, obviously this is a functional block, I can't do anything about it. I have to insert a little more buffers out here, right, or I need to modify this functional block and probably think of a different pipelining structure. So there is a setup slack violation out here, setup time violation. So how to compute setup slack, is it understood by all of you? Anybody has got any doubt?
Can you repeat again?
Yeah, okay, sure. See, this is the clock, okay. So how fast now I have to find out how fast the clock will come here and how late the data will come here, okay, to find out whether there is so that is the worst case scenario. Worst case scenario is clock is coming very fast and data is coming very slow. But even in the worst case scenario, the setup violation should not happen ideally. So I am talking about the worst case scenario with the fastest clock path. So between two clock pulses there will be 15 nanosecond delay. So I take that 15 nano. Time period is given 15 nano, 15 nano. This max and minimum is the path delay here. So I am taking the worst case scenario, fastest case here. So 2 nanosecond. This is 5 is the minimum, 9 is the maximum. So I am taking minimum in this path. Everything I am taking minimum 5 and then plus 2 and minus 4 is the setup. So this minus 4 is the setup. So now this is the clock has reached here. What about data? Data is I am talking now for the data. I am talking. I will take the slowest path. So 2 nanosecond plus 11 nano plus 2 plus 9 plus 2. So this. So I am getting it. If I take the difference, it is minus 6. So this is a setup time violation is there here. Is it okay now with all of you?
Yes, sir.
Okay.
Yes, sir.
Okay. Similarly, I have to check for hold. Okay. In the hold, I am assuming both the clocks are going high at the same state. Okay. I am talking about a single clock, right? Now, what is the for the whole time minimum time taken for the data? Okay. Now that I am going to take. So it is 1 nanosecond, right? From here to here 9 nanosecond, 1 nanosecond and 1 nanosecond. Okay, and then now it has to remain there, okay, till the clock is there. So I am adding this whole nanosecond, 1 nanosecond here, right? I am putting this 1 nanosecond catering for the 1 nanosecond. Okay, so this is the fastest data. Okay, 1 plus 9 plus 1 plus 6, 6 plus 1. Okay, fastest data. What about the clock here path? Now clock, I'll take clock for the worst case scenario. I have to cater for the max delay here. So I'm not talking about the time period here in the hold. If you see here, it is 3, okay, plus 9. Now worst case I am taking plus 3, right, plus 2 this whole time also, because this data requires to be. So this is plus 2 has come here. So you will see here it is 1 nanosecond. That means the clock can come here, okay, at around 17, including the hold, whereas the data will be there up to 18. Okay, that is including the hold time also. I am talking about it. So there is no issue with the hold time out here. So is it okay now how to compute the hold time? Right, here we are taking the minimum clock part delay. Here we are talking about minimum data and max clock. Okay, so this is swapped out here. So that is the difference out here. Is it okay?
So though we are computing the hold time for FF2, actually is it the hold time of FF1? Because
it could be different.
It has to retain the data.
No. We are looking at only one flip flop at the output flip flop as. See, these flip flops, this could be a T flip flop, not necessarily. So here we are only worried about the propagation time. Okay, that whole time is depending on this input. Okay, we are analyzing at this particular flip flop. For each flip flop, we are doing the analysis. Okay, this flip flop for us is only contributing towards the delay for analysis of this flip flop. We are not talking about the setup time and hold time of this particular flip flop, input flip flop. Okay, that depends on again data what is coming from the left hand side. Okay, we are focusing on this.
Clock to Q we have taken for FF1.
Only clock to Q. This propagation delays. Okay, for the setup time we will talk about the max time which is taken, and for the hold time we will talk about the minimum time which takes from here to here. That's all. Okay.
Sure, thank you.
Okay, so let's take one more example out here. Now I have a flip flop where there is some logic, and I have given back here. Okay, so in this case also, if you see here, the max clock frequency is the propagation delay of the flip flop plus the combinational delay plus the setup time. Okay, so the clock time period has to be greater than these three in this particular logic, isn't it? Like there is no hold delay here. Okay, the only setup will be available here in this particular case. The setup will be right. Once the data has changed, it has to reach here. How will it reach here? Clock has been given here, right? From T flip flop plus combinational logic plus the setup time also has to be catered for. So the maximum clock frequency which can be given here will be 1 by T here. This is the maximum clock frequency which I can give here will be 1 by T, where T is defined by this equation, right? This is a simple. Okay, I take one more example. I think with that we'll call it up for today. Take this particular circuit. Okay, now what about the given the flip flop setup time is 6 nanoseconds, hold is 2 nanoseconds, that is given. This propagation delay is 10 nanosecond. Calculate the minimum clock period required to handle. Okay, so what is the minimum clock period which we need to give? Okay, so this particular circuit is divide by 2. It is doing divide by 2. If you see here, clock is given here. So what is the minimum clock period? Okay, so T minimum has to be greater than T setup plus T clock plus T delay. Okay, delays from here to here. Now in this particular case there is no delay. I am just short circuiting the Q bar to Q. So this is 0. So T setup is 6 nanosecond. Once the clock is given, this D needs to come to Q bar, okay, so that is 10 nanosecond, and I have to cater for 6 nanosecond, so 16 nanosecond, so total 16 nanosecond, okay. So in many flip-flops, when I say, okay, T, C to Q, it also means C to Q bar, okay. Q and Q bar, they change simultaneously, okay. You have to take that as a okay, if it is given only D to clock to Q, okay, then you should not be wondering what will be clock to Q bar, okay. Clock to Q will be same as clock to Q bar also. So you will have, this is the minimum time period, so maximum frequency will be 1 by 16. Is this computation clear to all of you? Okay, so this is the minimum. Now, if I talk about hold time in this particular circuit.
Sir,
Yeah,
sir,
tell me.
Please repeat, sir, this T minimum when we are calculating.
Yeah.
And
T minimum is like once this clock
Q
is,
from the beginning.
yeah, when the clock is going high, right?
Yeah.
When the clock is going high, okay, D, okay, the data has to come from there to it has to get reflected at Q bar, okay. That is given by T clock to Q, okay. That is there. Now this data is readily available at D because I am not considering there is any delay in this wire, so that I am putting it 0. But this requires some that setup time is defined in this flip flop, so I have to cater for that setup time. So it becomes 6 plus 10, 16 nanosecond is the, once I have given a clock, I have to give the next clock after 16 nanoseconds only, out of which 10 nanoseconds is the time for Q bar to get settled, and 6 nanosecond is the time as a setup time we are giving for this flip flop. So that much buffer is being given as setup for this before the arrival of the next clock edge. So total 16 nanosecond, right? So that is the time between two positive edges of the clock minimum. If it is more, it doesn't matter. So that is the minimum. If that is minimum, F maximum will be 1 by 16. Is it okay now?
Yes. Thank you.
Okay.
Sir, clock to Q and clock to Q bar are same.
Yeah, clock to Q and clock to Q bar will be same. Okay. Okay. Now, when I talk about hold time also, right? When this clock is going high, right? So at least for, it says at least for 2 nanoseconds, this D requires to be stable, right? When the clock is going high, the input D requires to be stable at least for 2 nanoseconds. Okay, it can't change before that. Is that condition being met? It is met because D is going to get changed only after 10 nanoseconds. And what is 10 nanosecond? That is the delay from clock edge to Q bar change, right? So that is 10 nanoseconds. So there is adequate 8 nanosecond slack is available as far as hold slack is concerned. So that is no hold violation, and no slack is we are defining the minimum frequency. So there is no hold time violation also in this particular case. Is it okay? Why there is no hold time variation? Right? When the clock is going high, the data needs to be stable at least for 2 nanoseconds. Right? Whereas the data is going to change only after 10 nanoseconds. So that means propagation delay is inbuilt in this flip flop. So there is, you can very well connect it like this. Okay. So when you are making these kind of circuits, so you have to take care. Okay, depending on what kind of parameter is there. Suppose this hold time, for example, if this hold time is also 10 and the propagation is also 10, then I can't make these kind of corrections, right? So what will I do? I'll put a buffer out here, inserting more delay, 2 inverters, so that D doesn't change immediately, right? But by putting 2 buffers in between, this T minimum will increase, and hence I will have to use a slower clock in that particular case. So when we are designing these kind of circuits, we will do a static time analysis for every flip flop in the circuit. Okay. And if there is a violation of hold time or setup time, then accordingly buffers might have to be inserted in between. Okay. Is it okay with all of you? Okay. Then thanks a lot. We will stop it here. Yeah, tell me.
Sir, in this setup and hold time calculation, we are not considering the clock jitter, right?
Yeah, clock jitter will add additional clock jitter and buffer we have not done. But in case there is a clock jitter and buffer, we need to do that also. If it is given, then it will.
Okay. So, and one more thing, like we are considering the delay as 0, but practically the delay might be having some of the wiring delay as well, right?
Yeah, correct. In this particular case, we have not taken. In the previous example, where it is moving from one flip-flop through an inverter, this wire delays also we have taken care. Right?
Okay, sir.
Right?
Yeah.
In this particular case, it is from here to here itself. So, it might be negligible. Right? In this also, it depends on the problem which is given to you. So, in case there is wire delays to be neglected, somebody says, then you neglect it. If it is specified, then you need to take that. Okay, depending on the data which we have in hand, we have to do that. Okay.
Okay, sir. Got it.
Okay.
Thank you.
Okay. Thanks a lot. What I am going to do is, although in my web page last year's class are available. Even today's class also I'll keep putting it. I will add it as dash 2002 2022 so that these classes also will be available on my web page, as well as I am renaming these things in the team also, so that for ease of reference. Okay. Thanks a lot.
I have few questions.
Yeah.
Thank you.
Yeah. Will you be covering more advanced STA, for example, multi-cycle hold and reset removal, reset recovery?
No.
Or clock pulse weight check and all that?
No. STA we will stop it here. Right?
Okay.
Because of the that becomes too specific. Only those who are working in that domain will be able to follow it. But as a course, it would be difficult for a few people. Okay, and this itself will be slightly difficult for people who are new to this domain. But if you go further deep, it would become slightly difficult for people. Okay.
Yeah. And one question on previous lecture.
Yeah.
So I really like those advanced techniques actually. But using Verilog code, can we really code this pipeline structures or latch-based structures, or it should be a custom design altogether?
Not necessarily. I think Verilog code. I'm not very sure. I'll have to look whether already for those kind of flip-flop modules, whether such codes are available or not, or can you code. I have not come across anything like that, but there could be some code. I'll have to check on that aspect.
Yeah, if you have some sample, that will be really great. Yeah.
Okay. I'll have it.
Thank you, Professor.
Okay.
Thank you very much.
Okay.
Good night. Bye.
Good night.
Thank you.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.